Most people believe the smallest pieces of matter should be simple, isolated, and easy to point to. That belief is wrong. At the deepest level we can measure, the universe contains objects that can never exist alone, never be pulled free, and never appear by themselves anywhere in space. These objects are called quarks, and their behavior quietly breaks our everyday intuition about what real even means. Tonight we are not rushing. We are slowing down and looking carefully at what quarks actually are, how we discovered them, and why modern physics no longer treats them as tiny solid things, but as controlled disturbances inside powerful quantum fields. And before we can understand what quarks are made of, or whether they are even objects at all, we have to face a rule the universe enforces without exception. A rule so strict that no experiment, no collision, and no amount of energy has ever broken it. This is where part 1 begins. Why does the universe forbid a single naked quark from existing anywhere in space? No experiment in human history has ever seen a quark alone. And this is not for lack of effort, energy, or imagination. For more than half a century, physicists have smashed matter apart with increasing violence, concentrating energies high enough to briefly recreate conditions that last existed microseconds after the Big Bang. Yet every time, without exception, the universe responds with the same refusal. Quarks never appear in isolation. They emerge only in groups locked together so tightly that separation itself becomes impossible. This is not a technical limitation. It is a rule written into the structure of reality. To understand why this rule exists, we need to move slowly and carefully, because quark confinement is not an intuitive idea. In everyday life, if you pull hard enough, things eventually come apart. Molecules separate into atoms. Atoms can be stripped into electrons and nuclei. Even nuclei can be broken into protons and neutrons. Classical intuition suggests that if we keep going, if we apply enough force, something smaller must eventually be freed. But quarks violate this expectation completely. The story begins in the 1960s, when Murray Gell-Mann and George Zweig independently proposed that protons and neutrons were not fundamental, but made of smaller constituents. Gell-Mann called them quarks, borrowing a word from James Joyce, but the name quickly took on a very precise scientific meaning. At first, quarks were treated as a mathematical tool, a way to organize patterns seen in particle experiments. Many physicists did not believe quarks were real physical entities. The reason was simple: no detector had ever seen one. That skepticism did not disappear even after deep inelastic scattering experiments at the Stanford Linear Accelerator in 1968 revealed something remarkable. When electrons were fired into protons at extremely high energies, the scattering pattern showed that the proton was not smooth. It contained hard point-like structures inside. Richard Feynman called them partons. Later, it became clear that partons and quarks were the same thing. The proton truly had internal components. Yet even then, those components never escaped. This brings us to the first shock. In quantum chromodynamics, QCD, the theory that describes the strong force, the force between quarks does not weaken as they move apart. It strengthens. This is the opposite of gravity and electromagnetism, which fade with distance. In QCD, pulling quarks apart is like stretching an elastic band that becomes stiffer the more you stretch it. Energy does not disperse, it accumulates. At a certain point, the energy stored in the strong force becomes large enough to create new quark-antiquark pairs from the vacuum. Instead of freeing a quark, the universe creates more matter. The system reorganizes itself into new bound states called hadrons, particles like protons, neutrons, and mesons. The original quark remains confined, now paired differently but never alone. This phenomenon is called quark confinement, and it is not a hypothesis. It is an experimentally established fact. Every high-energy collision performed at particle accelerators confirms it. At facilities such as CERN's Large Hadron Collider, beams of protons are accelerated to energies of several tera-electron volts and smashed together. The collisions are violent beyond everyday imagination. Temperatures briefly exceed trillions of Kelvin, and yet the debris never includes a single isolated quark. Physicists can measure the aftermath with exquisite precision. They see jets of particles spraying outward from the collision point, and the structure of those jets matches exactly what QCD predicts when quarks attempt to separate and fail. The pattern is so consistent that confinement is now used as a diagnostic tool. If jets behave differently, it signals new physics. But the absence of free quarks remains absolute. What makes this even more unsettling is that nothing in the equations of QCD explicitly forbids free quarks in a simple, obvious way. The theory allows them mathematically, but the dynamics of the strong force make their isolation energetically impossible. This is one of those moments where physics stops feeling like engineering and starts feeling like law enforcement. The universe does not argue, it enforces. The mechanism behind this enforcement lies in the nature of the strong force itself. Unlike electromagnetism, which is mediated by photons that do not carry electric charge, the strong force is mediated by gluons that carry the very charge they interact with. This charge is called color, and it has nothing to do with visual color. It is simply a name for a three-valued quantum property. Because gluons carry color charge, they interact with one another. The force lines between quarks do not spread out like electric fields. They form narrow tubes of energy called flux tubes. When quarks are close together, the tube is short and the energy is modest. When you try to pull them apart, the tube stretches, storing more and more energy per unit length. This behavior has been confirmed not only in accelerators, but also through large-scale numerical simulations called lattice QCD. Using supercomputers, physicists discretize spacetime into a grid and calculate how quarks and gluons behave according to the equations of QCD. The results consistently show confinement emerging naturally from the theory. No additional assumptions are required. Here, the universe reveals something deeply counterintuitive. It allows quarks to exist. It allows them to move inside hadrons. It allows them to exchange momentum and energy, but it does not allow them to exist as individual objects. Isolation is not merely unlikely. It is dynamically forbidden. This rule has profound consequences far beyond particle physics. Without confinement, protons would not exist as stable entities. Atomic nuclei would not form. Chemistry would collapse. Stars could not burn in the controlled way they do. The entire chain of cosmic structure depends on quarks being permanently bound. Consider nuclear fusion in stars. When hydrogen nuclei fuse into helium, the energy released comes from changes in binding energy at the quark level. Quark confinement ensures that protons and neutrons behave as stable building blocks rather than dissolving into a sea of free constituents. Stellar lifetimes, measured in billions of years, depend on this stability. So does the slow, steady production of heavier elements. Even in extreme environments, confinement persists. In the early universe, during the first microseconds after the Big Bang, matter existed in a state called quark-gluon plasma. Quarks and gluons were not bound into protons and neutrons. They moved freely over short distances. But even then, they were not isolated. As the universe expanded and cooled below about 200 mega-electron volts, roughly 2 trillion Kelvin quarks became confined again. The transition was smooth, but the rule reasserted itself. Modern experiments recreate this plasma in heavy ion collisions at facilities like the Relativistic Heavy Ion Collider and the LHC. The plasma flows like a nearly perfect fluid. Yet when it cools, confinement returns instantly. No free quarks remain. This raises a question that cannot be ignored. Why does the universe care so much about preventing isolation at this level? Other forces allow individual charges to exist. We can isolate electrons. We can isolate photons. We can isolate neutrinos. But quarks are different. One possible explanation lies in the mathematical structure of non-abelian gauge theories, of which QCD is the prime example. The self-interaction of gluons creates a vacuum that is not empty, but structured. The vacuum itself resists the separation of color charge. In this view, confinement is not a property of quarks alone, but of space filled with quantum fields. Physicists continue to search for a complete analytic proof of confinement from first principles. Despite decades of effort, no simple proof exists. This is one of the Clay Mathematics Institute's Millennium Prize problems. The difficulty is not experimental. It is conceptual. The universe behaves one way, and our mathematics is still catching up. Richard Feynman once warned, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical." Confinement is one of the clearest examples of this warning. Classical intuition fails completely. Quantum fields, not particles, define what is allowed. What makes this rule especially unsettling is its universality. Confinement does not weaken in empty space. It does not depend on temperature once hadrons form. It does not care how violently you intervene. Machines stretching for kilometers, using energies unmatched anywhere else in the present universe, still cannot violate it. This suggests that confinement is not a local constraint, but a global one. It is not something imposed externally. It is built into how quantum chromodynamics organizes reality. And yet, questions remain open. Could confinement break down at scales or conditions we have not yet reached? Could new physics beyond the standard model modify this rule? Could quarks themselves be composite, with confinement emerging from an even deeper layer? Every test so far says no. But physics advances precisely by asking where rules might fail. If quarks cannot exist as isolated objects, then perhaps they are not objects at all, in the way we normally understand them. And that realization quietly prepares the ground for the next layer of the story, where the very meaning of particle begins to lose its solidity. Part 2. Are quarks objects at all, or merely tension knots in an invisible cosmic field? If you try to picture a quark as a tiny bead hidden inside a proton, you have already stepped into the trap that modern physics spent the last century escaping. In everyday thinking, what something is usually means what it is made of, and what it is made of usually means smaller pieces you could, in principle, separate and hold apart. Part 1 showed why quarks refuse that picture in the most direct way possible. No single quark has ever been isolated. But Part 2 goes deeper than the laboratory result. It asks whether object is even the right category for a quark in the first place, or whether a quark is better understood as a particular kind of organized activity inside fields that fill all of space. This is not wordplay. It is a practical question that working physicists confront every time they calculate what a detector should see. Start with the cleanest statement we have about how particle physics works today. The standard model is written as a quantum field theory. In that framework, the primary entities are not little balls moving through empty space. The primary entities are fields. Each field is defined everywhere, including in regions where there are no particles present. A particle is what we call a localized, quantized excitation of a field, a specific packet of energy and momentum that behaves in a repeatable way when it interacts with other fields. This is not a philosophical preference. It is the language that makes the predictions line up with experiments. Quarks are the sharpest test of this idea because their particle-like aspects are real and measurable, yet their object-like aspects fail at the exact moment you try to treat them as separable pieces of matter. In the standard model, quarks are excitations of quark fields. They carry electric charge spin and a strong interaction charge called color. They interact by exchanging quanta of the gluon field. All of that sounds like ordinary particle talk. The difference is what happens when you try to define a quark as something you could take out of the field and place on its own the way you can trap an electron. The theory itself blocks that move, because color-charged excitations do not propagate as free, isolated states at low energies. Instead, they are confined into composite states hadrons, whose overall color cancels. This is where Richard Feynman's warning becomes a useful guide rather than a slogan. He did not need quarks to say it, but quarks make it unavoidable. In one of his plain-spoken remarks about the mismatch between everyday intuition and quantum reality, he said, "I think I can safely say that nobody understands quantum mechanics. Quarks are a reason that sentence remains alive, not because quarks are mystical, but because they force us to be precise about what we mean by thing. The path to this precision runs through an experiment that looks simple from the outside. In the late 1960s at SLAC, electrons were scattered off protons at high energy. If the proton were a smooth blob of charge, the scattering would look like light diffracting through a soft object. Instead, the scattering indicated that the electron was bouncing off point-like constituents inside the proton. The data showed patterns that were later understood in terms of parton distribution functions, probabilities, describing how the proton's momentum is shared among its internal constituents. The result was an operational picture. Inside the proton there are components that act point-like when probed at short distances. That short distance detail matters. It is exactly where quarks behave most like objects. In quantum chromodynamics, the strong interaction becomes weaker at shorter distances. This is asymptotic freedom, the discovery that earned David Gross, Frank Wilczek, and David Politzer the Nobel Prize in the early 2000s. The meaning is practical. If you probe a proton at a high momentum transfer, you are looking at distances so small that the quarks interact less strongly over the brief timescale of the collision. For that instant, the quark behaves like a nearly free particle. This is why the parton model works, why the proton can be treated as having constituents, and why high-energy scattering can be calculated with remarkable accuracy. But the same theory predicts the opposite at larger distances. As you move to longer scales, the strong interaction grows. The gluon field does not simply mediate forces the way the electromagnetic field does. Gluons carry color themselves, so the field interacts with itself. The result is that energy in the strong field does not spread out as a fading influence. It concentrates into narrow structures called flux tubes. When you try to separate color charge, you are not opening empty space between two objects. You are stretching the field into a higher energy configuration. At some point, it becomes energetically favorable for the field to produce a new quark-antiquark pair, turning one attempted separation into two color-neutral bound states. You do not get a free quark. You get more hadrons. So the laboratory story already points to a field-first view. A quark is not a bead you can remove from matter. It is a particular way the quark field and gluon field can be excited together inside a bound system. The thingness of the quark is scale-dependent. At high energies and short distances, you can treat quarks as if they were individual constituents. At low energies and long distances, the universe makes you describe what you see in terms of color-neutral composites. This scale dependence is not a defect. It is one of the main working ideas in modern physics. Physicists call it effective description. When you look at a fluid, you talk about pressure and flow, not about the motion of every molecule. When you look at a crystal, you talk about vibrations and collective modes, not about tracking every electron one by one. In particle physics, when you look at hadronic matter at low energies, you talk about hadrons and their interactions because those are the stable, observable excitations in that regime. At higher energies, you can resolve quarks and gluons as effective degrees of freedom. Both descriptions are correct within their domains. This is where the question in the title becomes concrete. Are quarks objects at all, or are they organized stress in fields? In QCD, the energy of a bound hadron is not simply the sum of the masses of its quarks. Most of a proton's mass is not the bare masses of the up and down quarks. It comes from the energy stored in the gluon field and the kinetic energy of confined quarks, along with effects tied to the structure of the QCD vacuum. You can treat that as a bookkeeping statement, but it has a physical meaning. When you hold a proton in your hand, the mass you attribute to it is largely the energy required to sustain a particular stable pattern in interacting quantum fields. The proton is not a bag of parts. It is a persistent field configuration with properties that remain stable across time and across environments. To make this idea feel less abstract, notice how detectors actually work. A modern particle detector does not take a photograph of a quark. It records tracks, energy deposits, timing, and patterns of secondary particles created when an unstable configuration decays or hadronizes. In high-energy collisions, quarks and gluons are produced in the early stage, but what reaches the detector are jet sprays of hadrons, whose statistics encode the earlier quark and gluon dynamics. The connection between early-stage quarks and late-stage hadrons is modeled through QCD calculations and hadronization models that are tuned and tested against data. The quark is present in the theory because it is the right internal variable to predict what the detector sees, not because it is a tiny object that ever arrives intact at the sensor. This is also why the word particle itself needs careful handling. In quantum field theory, a particle is a well-defined concept when the field interactions are weak enough that you can identify stable excitations that travel long distances without mixing. Photons and electrons satisfy this extremely well. Neutrinos do so with their own subtleties. Quarks do not, because the strong interaction never lets a color-charged excitation become an isolated, long-lived asymptotic state at the energies where matter exists around us. So when someone asks what is a quark really, a scientifically honest answer begins with the operational layer. A quark is a fundamental fermionic field excitation in the Standard Model that carries color charge and participates in the strong interaction described by QCD. That statement is not a slogan. It tells you what equations govern quarks, how they interact, and why they appear as constituents inside hadrons. It also tells you why they are never observed as free particles. Then the deeper layer arrives without needing metaphors or mysticism. In the framework that best matches experiments, quarks are not building blocks you can separate and stockpile. They are permitted patterns in fields, patterns that can only appear in certain combinations, because the field theory enforces color neutrality in observable states. If you insist on calling them objects, they are objects with a boundary condition imposed by the theory itself. They can exist only inside a larger color-neutral structure. There is a historical reason this conclusion feels unsettling. For centuries, science progressed by reducing complex things to simpler parts, atoms to electrons and nuclei to protons and neutrons. The expectation becomes a habit, but the strong interaction breaks the habit. It gives us constituents that reveal themselves in high-energy probes, yet refuse to appear as free fragments. The universe allows us to infer quarks from scattering data with precision, to measure how they share momentum inside a proton, to test QCD through jet production and scaling behavior, and to compute hadron properties through lattice simulations. It also refuses to let us pick up a quark and treat it as a standalone ingredient. That refusal is not a barrier to knowledge. It is a piece of knowledge. It tells us that the deepest descriptions may not be about solid components in empty space, but about fields whose allowed excitations depend on how those fields bind, screen, and reorganize energy. Quarks behave like particles when you probe them at short distances, and they behave like inseparable patterns in interacting fields when you try to treat them as standalone objects. Both behaviors are the same theory seen at different scales, and if that is true, then the next step cannot stay inside the proton for long, because there was a time when the universe itself was hot enough that quarks and gluons were not packed into hadrons, and the only way to understand why matter survived at all is to return to that early interval and ask why the cosmos ever left that plasma state behind. Part 3. Why did the early universe choose quarks instead of pure radiation? In the first microsecond after the Big Bang, the universe was so hot that the idea of an atom was not just impossible, it was meaningless, and yet in that heat, a set of rules took hold that would later decide whether anything like matter could persist at all. To place your mind there, it helps to start with what we can measure now, because modern cosmology is built on a careful chain from present evidence back to early conditions. NASA and ESA missions have mapped the cosmic microwave background to the afterglow of the early universe with such precision that we can infer the universe's basic composition, its geometry, and the tiny variations in density that later grew into galaxies. That afterglow comes from a later time, about 380,000 years after the beginning, when the universe cooled enough for electrons to bind to nuclei and let light travel freely. But the logic does not begin there. Long before the first atoms, there was a period when the dominant content of the universe was radiation, and embedded inside that radiation was a seething mixture of quarks and gluons. The reason this matters is that radiation and matter are not just different labels. They behave differently as the universe expands. Radiation loses energy faster because its wavelength stretches with expansion. Matter, once it exists as massive particles, dilutes mainly by spreading out. If the early universe had remained pure radiation in the sense of never forming stable, massive building blocks, the later story would look radically different. There would be no enduring nuclei, no long-lived baryons like protons, and no platform for chemistry. The question in this part is not a poetic one. It is a technical question about phase transitions, cooling rates, and the specific properties of the strong interaction. When cosmologists talk about the first microsecond, they are pointing to the era when the temperature of the universe was of order trillions of Kelvin. Your original prompt gives a value that is often quoted in popular descriptions about 4 trillion Kelvin, which corresponds to energies where quarks and gluons are not confined into protons and neutrons. At those temperatures, matter was not arranged as discrete particles in the way we experience it. It was closer to a plasma, but not the plasma of electrons and ions in a fluorescent lamp. It was a quark-gluon plasma, a state in which quarks and gluons are the active degrees of freedom over short distances. This is where the strong force becomes the central actor. In Part 1, you used the word confinement, and that word is the key. Today, confinement means that quarks do not appear as isolated particles. They are bound into hadrons. But confinement is not a static rule in all environments. It depends on energy scale and temperature. Quantum chromodynamics predicts that at very high temperatures and densities, the effective behavior changes. Quarks and gluons can move over distances that are larger than they can inside a cold proton. In practical terms, the locking that holds quarks inside hadrons becomes weakened by the surrounding energy density. How do we know this is not just theory? Because we can test parts of it in the laboratory, and we can test other parts through cosmological observations. On the laboratory side, heavy ion collision programs were built for precisely this purpose. At the relativistic heavy ion collider, gold nuclei were accelerated and collided, and at CERN's Large Hadron Collider, lead ions have been collided at even higher energies. Detectors such as ALICE were designed to reconstruct the thousands of particles produced in each event, and infer the properties of the short-lived state created immediately after impact. The surprising result, reported consistently across many measurements, is that the quark-gluon plasma behaves like a strongly coupled fluid with very low viscosity. It flows collectively. It produces patterns called elliptic flow, which indicate that the matter created is not a weak gas of free quarks, but a dense interacting medium. That is a crucial detail. The early universe was not quarks flying independently through empty space. It was quarks and gluons in a crowded environment where interactions were constant. On the cosmology side, the early universe's expansion rate is anchored by well-tested physics. Once you accept the measured expansion history and the basic thermal model, temperature and time are linked in a predictable way during the radiation-dominated era. The universe cools as it expands, not because it loses heat to space, but because the energy density drops and the typical particle energies fall. In that cooling, there are thresholds. When the temperature falls below certain energies, new stable forms of matter become possible. Quark confinement is one of those thresholds. The question then becomes precise. Why does the universe end up with quarks confined into hadrons, rather than remaining in a long-lived, deconfined state? The answer is not a choice in a human sense. It is a thermodynamic transition governed by QCD. At extremely high temperature, the free energy of the system is minimized in a deconfined phase. As the temperature falls to around a few trillion Kelvin, the confined phase becomes favored. The degrees of freedom change. Instead of quarks and gluons being the convenient variables, hadrons become the stable excitations. In many descriptions, you will hear that this transition happens around a temperature of roughly 2 trillion Kelvin, often associated with an energy scale on the order of 150 to 200 mega-electron volts. The exact character of the transition depends on details like baryon density. In the early universe, the baryon density was very small compared to the photon density, so the transition is expected to be a smooth crossover rather than a sharp first-order jump. That distinction matters because it affects whether you would expect dramatic relic signatures like strong gravitational wave bursts from bubbles of phase transition. In the standard picture, the QCD transition is not expected to leave a large, easily detectable gravitational wave background, but it still matters because it sets the stage for what comes next. Now slow down and notice something that is often missed. This is not just quarks became protons. The transition reorganized the entire inventory of what counted as a stable unit. Before confinement, the universe had an enormous number of degrees of freedom available to store energy, because quarks, antiquarks, and gluons can exist in many color and flavor states. After confinement, many of those degrees of freedom are no longer available as separate carriers. Energy that used to be distributed across a sea of quarks and gluons becomes concentrated into hadrons and into radiation. That changes the relationship between temperature, pressure, and expansion, even if subtly. Cosmologists model this through the effective number of relativistic degrees of freedom, which influences how quickly the universe cools during radiation domination. So the phrase quarks froze out of chaos can be stated in more concrete terms. As expansion cooled, the universe reaction rates eventually fell relative to the expansion rate, and the system's equilibrium composition shifted. Above the confinement temperature, it is natural for quarks and gluons to be present as the main players. Below it, the energetically favored stable excitations are color-neutral hadrons. Once hadrons dominate, you now have a kind of matter that can persist as identifiable units while the universe continues to expand. This is also the moment when the idea of radiation only loses its grip. Even if radiation remains dominant in energy density for a long time afterward, the appearance of stable hadrons creates a separate bookkeeping category. You now have baryons, and baryons can later take part in nucleosynthesis. This leads to the next crucial interval, a few minutes after the beginning when protons and neutrons fuse into light nuclei. The predicted abundances of hydrogen, helium, and traces of deuterium and lithium depend on the balance between expansion and nuclear reaction rates. The success of Big Bang nucleosynthesis is one of the strongest arguments that the thermal history is broadly correct. It is one of the reasons cosmologists take the early universe timeline seriously. There is a historical arc here worth holding on to because it shows how this picture became credible. In the 1940s, George Gamow and his collaborators explored the idea that the early universe could act like a nuclear reactor, producing the light elements. This was not a complete modern calculation, but it set the direction. Decades later, the discovery of the cosmic microwave background by Penzias and Wilson in the 1960s gave the hot Big Bang model its observational anchor. Later still, satellites such as COBE, WMAP and Planck measured the background spectrum and anisotropies, with increasing precision allowing cosmologists to extract parameters that make the whole thermal history internally consistent. None of this directly images the first microsecond, but it constrains the conditions under which that microsecond could have occurred. Even NASA and ESA observatories that look at galaxies including JWST connect indirectly to this early phase. JWST's observations of very early galaxies test how quickly structure formed, and structure formation depends on the nature of matter. If the early universe did not produce stable baryons, the later pathway to stars and galaxies would be broken. In that sense, every deep image of early cosmic history rests on the microscopic fact that confinement occurred and hadrons became stable building blocks. A careful listener might now raise a hard question, and it is worth raising with respect. If the early universe was hot enough for quark-gluon plasma, why did that plasma not simply persist as expansion continued? Why did it not remain as deconfined quarks and gluons, only cooler? The answer lies in the coupling of QCD. As the energy scale drops, the strong interaction becomes stronger. At low energies, the theory does not permit color-charged excitations to remain as free states. Confinement is the low-energy behavior. Cooling is not just lowering speeds. It is moving the system into a regime where the fundamental interactions reorganize what stable means. Another challenge comes from the word choose. In physics, the universe is not selecting outcomes the way a person selects an option. But the language can still be useful if we translate it into dynamics. What actually happens is that the system follows the path of lowest free energy available under the constraints of expansion. If you want a concrete mental image, imagine a landscape where the stable arrangement changes as temperature changes. At very high temperature, the lowest point corresponds to deconfined quarks and gluons. As the temperature falls, the shape of the landscape changes, and the lowest point shifts toward confined hadrons. The system rolls toward that new stable configuration, because that is what equilibrium means in thermodynamics. This is also where the laboratory work earns its value. Heavy ion collisions do not recreate the early universe's expansion history, but they recreate the relevant temperatures and energy densities for an instant. The fact that QGP can be produced and its properties measured gives confidence that QCD actually has the phases cosmologists rely on. It ties the early universe story to tangible evidence rather than to extrapolation alone. Now fold in one more critical point. The early universe contained both matter and antimatter in enormous numbers. At those temperatures, particle-antiparticle pairs are created and annihilated constantly. If the universe had perfect symmetry between matter and antimatter, most of it would annihilate, as cooling made pair production less efficient, leaving behind radiation with almost no baryons. The reason we can talk about protons remaining at all is because there was a tiny imbalance, roughly one extra baryon for about 1 billion photons. That imbalance is not explained by confinement itself, but confinement is the stage on which the imbalance becomes meaningful. Once hadrons form, the leftover baryons become durable carriers of that asymmetry. So part 3 is doing two jobs at once. It explains why the early universe could contain quarks and gluons as an active phase, and it explains why the universe transitions out of that phase as it cools. The mechanism is QCD tested in accelerators and supported by numerical calculations. The consequence is that stable baryonic matter becomes possible. The observable legacy is that later processes from nucleosynthesis to the cosmic microwave background to the formation of galaxies have a consistent foundation. If you keep this chain in mind, the early universe stops feeling like a distant, untestable speculation. It becomes a connected narrative of constraints. The cosmic microwave background constrains the later conditions. Nucleosynthesis constrains the minutes. QCD constrains the microseconds. Heavy ion collisions test the QCD phase behavior. And the universe we see filled with atoms and stars is the downstream result. The mass of the proton is not mainly the mass of its quarks. The proton's mass is largely energy stored in fields and motion under confinement. That means the transition that created stable hadrons did more than create particles. It created a dominant reservoir of mass energy in the form we call matter, built largely from confined dynamics, rather than from bare constituent masses. And that leaves a sharp thread to pull next. A proton weighs close to 1 giga-electron-volt, but the quarks inside contribute only a small fraction of that. Part 4. How can almost all mass come from quarks that barely have any? A proton carries almost all the mass of the everyday world. Yet if you add up the masses of the quarks inside it, you do not even come close. And that mismatch is not a small rounding error. It is the central clue to where ordinary mass actually comes from. Let's anchor the numbers first, because the numbers are where confusion usually begins. The proton's rest energy is about 938.272 MeV, which is 0.938 GeV. If you translate that energy into kilograms, it is roughly 1.67 times 10 to the power of negative 27 kilograms. That single value repeated across every hydrogen atom in the universe is the weight-bearing element of stars, planets, oceans, and biology. Now compare it to the quarks that define the proton's identity. The proton is made from 2 up quarks and 1 down quark, but their intrinsic masses are only a few MeV, each far below 1 GeV. The exact values depend on the convention and the renormalization scale used in quantum chromodynamics, but the conclusion does not depend on details. The sum of bare quark masses accounts for only a small fraction of the proton mass. Most of the proton's mass is not sitting inside it as stuff. It is present as energy. This is the point where many explanations go wrong, by trying to make the answer sound simple. The real answer is simple in one sense, but it is not simplistic. It is that the strong interaction does not just glue quarks together. It stores energy in a way that becomes mass, and it does so persistently, in a stable configuration that we recognize as a proton. If you want the cleanest statement from a primary source, Frank Wilczek says it in his Nobel lecture with almost no decoration. Indeed, the mass of ordinary matter derives almost entirely from energy. The energy of massless gluons and nearly massless quarks. That is not a metaphor. It is a compact summary of the modern QCD picture. To make that statement feel concrete, take one step back to Einstein's mass-energy equivalence. Einstein described the equivalence as the most important upshot of the special theory of relativity. In daily life, it is easy to treat mass and energy as different categories, because most objects do not change their internal energy by a large fraction of their rest mass. But in strongly bound systems, internal energy is not a small correction. It is the main term. A proton is an extreme example of that rule. It is a small region where quantum fields carry enormous energy density in a stable pattern. The words quantum fields matter here because the strong interaction is not a mechanical pulling force between three beads. In quantum chromodynamics, quarks carry a charge called color, and they interact by exchanging gluons. Unlike photons, gluons themselves carry color charge, which means the gluon field interacts with itself. That single fact changes everything about how energy is arranged. It is the reason the strong interaction forms narrowed tubes of field energy, rather than spreading out like an electric field. And it is a major reason confinement exists at all. It is also the reason energy can be trapped in a compact region without being radiated away as free, long-lived quanta. You can see the consequences of this in modern experiments, but the important point is not that we see gluons directly. The point is that the patterns in scattering jet formation and hadron production match the predictions of QCD when you treat the proton as a bound state whose mass is largely field energy. CERN's public explanations of the Standard Model emphasize that the strong force is carried by the gluon. That is a short sentence, but behind it is a deep physical idea. When gluons carry the interaction, and also interact with one another, the vacuum and the bound states built on it become structured. The proton's mass is one of the measurable outcomes of that structure. Now, what does energy trapped inside a proton actually mean, in terms a listener can picture without equations? Imagine trying to confine something that must remain quantum mechanical. Quarks inside a proton cannot sit still in the classical sense. If you localize a particle into a region as small as a proton, roughly a femtometer across, you force it to carry significant momentum. Momentum implies kinetic energy. Even before you account for the gluon field confinement creates motion. Not motion as a trajectory you could draw, but motion as a persistent distribution of momentum inside the bound state. This is why the phrase trapped motion is physically accurate. The confinement scale sets a natural energy scale, and that scale is hundreds of MeV already comparable to the proton mass. But that is still not the whole story because the gluon field energy is not a minor addition. In QCD, the color field between quarks does not dilute as separation grows. It concentrates. That is why pulling quarks apart creates more hadrons rather than isolated quarks. Inside a proton, the same field concentration means that energy is stored continuously in the interacting quark-gluon system. The proton is not three quarks with a bit of binding energy around them. It is a strongly coupled many-body system, where quarks and gluons are constantly exchanging energy and momentum, and where the total energy in the rest frame is what we measure as the proton's mass. A useful historical comparison comes from the first time physicists realized that mass can be missing or gained without changing the list of constituent particles. In the early 20th century, careful measurements of atomic masses showed that the mass of a bound nucleus is less than the sum of the masses of its separated protons and neutrons. That difference is the nuclear binding energy released in fission and fusion. The proton is like a deeper version of that lesson. Nuclear binding energies are typically MeV per nucleon. Proton binding and confinement energies live at hundreds of MeV. The same logic applies. Bound systems have a mass that reflects the total energy, not just the ingredient list. If you're listening closely, a challenge may already be forming, and it is worth stating plainly. If most of the proton's mass is energy, why do we not see the proton radiating that energy away? Why does it not cool or decay the way an excited atom emits light and relaxes? The reason is stability. The proton is not an excited state that can drop to a lower energy configuration by emitting a photon. The proton is the lowest energy color-neutral baryon state, consistent with its quantum numbers in QCD, and there is no lighter state with the same conserved properties that it can decay into through the strong interaction. In that sense, the energy is not stored temporarily. It is the rest energy of the stable configuration. Another challenge appears when people bring the Higgs field into the discussion, because the Higgs mechanism is often described as giving mass to particles. That statement is correct for elementary particles in the Standard Model. Quarks do acquire their intrinsic masses through interactions with the Higgs field. But the proton is not elementary. It is composite, and its mass is dominated by QCD dynamics. So both ideas are true at once, and the distinction matters. The Higgs sets the baseline masses of quarks and leptons. QCD builds most of the mass of protons and neutrons out of energy in confined fields and motion. Wilczek's paper on the subject emphasizes that most of the mass of standard matter, by far, arises dynamically from back reaction of the color-gluon fields of quantum chromodynamics. You might wonder how we can claim such a statement with confidence, given that QCD at low energy is famously difficult to solve analytically. The answer is that the difficulty is real, but it is not a barrier to quantitative calculation. One of the great technical achievements of late 20th century physics was lattice QCD, where spacetime is represented on a grid and the theory is solved numerically using supercomputers. These calculations can reproduce hadron masses from first principles with impressive accuracy, including the proton mass when the input parameters are set by independent measurements. That is a key point. The proton mass is not merely fitted. It is emergent from the theory's dynamics under controlled computation. At this stage, it helps to connect the microscopic story back to cosmology, because this series is not only about what happens inside a proton. It is about what kind of universe you get when protons have the mass they do. In the early universe, once quarks became confined, and baryons formed, the mass budget of ordinary matter became dominated by these QCD-generated rest energies. That matters for the expansion history, for the timing of matter-radiation equality, and for the growth of structure. NASA and ESA missions that measure the cosmic microwave background constrain the density of baryonic matter precisely, and that baryonic density is largely the density of proton and neutron rest mass, which is largely QCD energy. The observational window is cosmological, but the mass being counted is hadronic mass. JWST sits much later in time observing galaxies when the universe was young, but it still depends on the same foundation. Galaxies form because matter clumps gravitationally. The strength of that clumping depends on how much mass ordinary matter actually carries. If protons were dramatically lighter, the chemistry and cooling pathways of gas clouds would change the balance of radiation, pressure, and gravity. Inside stars would shift, and stellar lifetimes and luminosities would be different. The details would be unfamiliar. The familiar cosmos filled with long-lived stars and stable atoms is compatible with a proton mass set mainly by QCD dynamics, not by quark bare masses alone. This brings us to a statement that feels almost too sharp until you sit with it. The proton's mass is a record of confined field energy. It is not an arbitrary property. It is an outcome of the strong interaction behaving the way it does in our universe. The fact that we can write 0.938 GeV and then trace that value into the behavior of stars, chemistry, and cosmic structure is one of the most practical examples of unity between particle physics and cosmology. There is also a subtle point that prevents a common misunderstanding. When we say mass comes from energy, we are not saying that mass is vague or optional. Mass is measurable. The proton's mass energy is measured with extraordinary precision. What changes is the accounting of where that measured quantity resides. It resides in the total energy of the bound state at rest, including field energy, kinetic energy, and the structure of the QCD vacuum. This is why the phrase "born from trapped motion and pressure" is not a flourish. Pressure is a physical concept in field theory, and in many body systems. The internal stresses of the confined quark-gluon system contribute to the energy-momentum content of the proton. In general relativity, energy momentum is what gravity responds to. In that sense, the proton's mass is not only an inert label, it is a contribution to the gravitational mass density of the universe. If you want one more experimental anchor that keeps the discussion honest, look at how the proton is probed at different momentum scales. At higher energies, the proton looks like a sea of quarks and gluons carrying fractions of its momentum, and the distributions evolve with energy scale, in a way predicted by QCD. At lower energies, the proton behaves like a stable particle with a fixed mass and size, participating in nuclear binding. Both descriptions agree on the same measured rest, mass. The difference is what degrees of freedom are most useful at a given scale. So what becomes clear at the end of Part 4 is not that quarks are unimportant. They matter in a very specific and limited way. They set the quantum identity of hadrons, and they define how the gluon field is allowed to organize itself. But the mass we measure is not a simple sum of quark masses. Most of it comes from the energy stored inside a confined interacting system. Once this picture settles, another detail becomes harder to ignore. Nature does not stop with two light quarks. It also produces heavier versions, strange charm bottom and top particles that appear only when conditions become extreme and then disappear again just as quickly. And that leaves us facing the next problem without any decoration. If the visible universe is built almost entirely from up and down quarks, why does the standard model contain 4 additional quark flavors that rarely appear yet emerge every time energy crosses the right threshold? Part 5. Why does nature need 6 quarks when only 2? Build the visible universe. The visible universe is built mostly from 2 quarks, yet the standard model insists on 4 more that appear only when you push nature into extremes. And that mismatch is not a detail. It is a warning that ordinary matter is only one thin operating mode of a much larger system. If you look around your room, almost every stable atom is made from protons and neutrons, and those are built primarily from up and down quarks. That is the practical truth of chemistry and biology. But in high-energy experiments, and in the earliest moments after the Big Bang, nature behaves as if 2 quarks were never the full story. The quark family comes in 6 flavors grouped into 3 generations. Up and down form the first generation. Charm and strange form the second. Top and bottom form the third. The first generation is enough to assemble nearly all stable matter we see today. So it is reasonable to ask why the other 4 are present at all, and why they appear with such consistency whenever energy and temperature reach the right thresholds. There is a historical reason this question feels sharp. The extra quarks were not invented to complete a pretty pattern. They were forced into existence by data, one discovery at a time, each one arriving as a correction to what physicists hoped would be the final list. The trail begins before quark was even a common word, with particles that behaved like they were trying to tell us the list was incomplete. In the 1950s, experiments found strange particles produced readily in high-energy collisions, yet decaying more slowly than expected. The strange behavior was not a poetic label. It was a measurable anomaly in decay rates and production patterns. To keep the bookkeeping honest, physicists introduced a quantum number called strangeness, and later the strange quark provided a clean structural explanation. The strange quark is heavier than up and down, so it is not common in ordinary nuclei, but it becomes accessible when collisions supply enough energy to create it. The universe did not add strangeness as decoration. It revealed a new kind of constituent that only becomes relevant in certain regimes. By the 1960s, the quark model had become a powerful organizing principle. but many physicists still treated quarks cautiously, as if they might be mathematical placeholders rather than real physical degrees of freedom. Murray Gell-Mann's own wording captures that caution. In his 1964 paper, he wrote, "It is fun to speculate about the way quarks would behave if they were physical particles instead of purely mathematical utilities." That sentence is not a retreat. It is the correct scientific posture at the time, because experiments had not yet shown the decisive evidence that quarks behave like point-like constituents under hard probing and confinement made it impossible to see them as isolated particles. Then came the event that changed the tone of particle physics almost overnight. In November 1974, two groups announced the discovery of an extraordinarily narrow resonance, the J-psi particle, found independently at Brookhaven and at SLAC. The episode is now called the November Revolution because it rapidly reorganized the Standard Model's credibility and direction. The CERN Courier account summarizes the outcome in plain terms, noting that it became clear that J-psi was the first example of charm bound with its antiquark, and that this was a vital step in building the Standard Model. The narrow width mattered because it implied an unexpectedly long lifetime for such a heavy state, which in turn signaled new selection rules and a new quark flavor. Charm was not an optional addition. It resolved multiple tensions in the theory at once, including problems with weak interaction structure that were becoming hard to ignore. A few years later, in July 1977, another heavy resonance appeared at Fermilab, a bump around 9.5 GeV in the distribution of muon pair events, later understood as the upsilon particle, a bound state of a type, bottom quark, and its antiquark. This was not merely one more particle. It was the opening of a third generation, because bottom does not fit into the same doublet structure as the first two generations, without bringing along a partner. The data kept making the same demand. If one member of a generation appears consistency points toward the other, the last quark top took longer, not because nature was reluctant, but because top is heavy enough that producing it requires far higher energies and enough collision statistics to separate signal from background. The discovery was announced in 1995 by the CDF and D0 collaborations at Fermilab. Fermilab's own newsroom record preserves a key feature of how discovery actually happens in a modern collider program. We discovered the top quark, not in one lightning stroke, but over a long period of time, is the message repeated in historical accounts. And the Fermilab release emphasizes the shift from evidence to discovery after much larger datasets, with CDF spokesperson noting they had previously stopped short of claiming discovery until the analysis confirmed it. The top quark did not arrive as a single dramatic event. It arrived as a statistical conclusion that the universe kept supporting. So 6 quarks are not a design choice made for elegance. They are a record of what experiments forced into the model. Now, the harder part is not the list. It is the reason the list has the structure it does. Why 3 generations? Why paired flavors? Why such a wide spread in masses from a few MeV for up and down to around 173 GeV for top? One way to approach that question, without drifting into speculation, is to focus on what the Standard Model must accomplish to remain internally consistent and consistent with data. The electroweak interaction organizes quarks into left-handed doublets, up pairs with down, charm pairs with strange, top pairs with bottom. This pairing is not cosmetic. It is how quarks participate in the weak interaction. It is also why quark flavors can change in certain decays, and why the CKM matrix exists as a measured description of how quark weak interaction states mix. You do not need the matrix elements to feel the consequence. If quarks did not mix, many observed decay patterns of hadrons would be wrong. The pattern of mixing is measured precisely in experiments studying kaons, B, mesons, and many other systems. The second and third generations are essential to reproduce the full landscape of weak decays. There is another reason the extra generations matter, and it connects directly to cosmology. The early universe did not always look like the universe today. In the first microseconds after the Big Bang, the temperature was high enough that heavier quarks could be produced abundantly as part of the thermal soup, even if they later disappeared as the universe cooled and expansion diluted. Energies. In that era, the inventory of active degrees of freedom changes the energy density and the expansion rate slightly. This is part of the reason cosmologists speak carefully about the effective number of relativistic degrees of freedom when they model early universe evolution. The details of QCD and the particle content influence how the universe cools through key thresholds, including the quark-hadron transition, discussed in Part 3. The extra quarks also leave fingerprints in astrophysical and laboratory environments that are extreme but real. Strange quarks, for example, can appear in dense nuclear matter through the formation of hyperons, and are discussed in the context of neutron star interiors, where densities can exceed nuclear density. This remains an active research frontier because it ties QCD at high density to astronomical observations of neutron star masses and radii. It is not necessary to claim a final answer about strange matter to see why the strange quark matters. The existence of strange quarks makes additional states of dense matter possible, and the universe supplies environments where those states might be realized. Charm and bottom appear routinely in high-energy collisions. Their bound states and decay patterns are used as precision tests of QCD and of the weak interaction. The existence of these heavy flavors allows physicists to probe the strong force across different mass scales and to test how confinement and hadronization behave when quark masses are large compared to the QCD scale. In this sense, the extra flavors are not unused. They are a laboratory built into the standard model, providing multiple ways to stress test the same underlying interactions. Top is different again. It decays so quickly that it does not form long-lived hadrons the way bottom and charm do. That makes the top quark a kind of direct window into bare electroweak decay dynamics, less masked by hadronization. The top mass is also so large that it plays an outsized role in precision tests of the standard model and in discussions of vacuum stability when combined with the Higgs mass. Even if one avoids speculative conclusions, the practical point remains. Top is not an ornament. It is a parameter that influences how the standard model fits together under precision scrutiny. The phrase in your outline, that these flavors appear only in extreme conditions, measured in tera-electron volts, is directionally right for top and for many production modes at modern colliders. But it is useful to separate flavor mass threshold from collider beam energy. Bottom quarks can be produced at energies far below a tera-electron volt in the center of mass of the relevant parton collision, because the mass scale is a few GeV. Charm is lighter still, and strange lighter than that. What modern tera-electron volt colliders provide is not merely the threshold, but enormous production rates, cleaner statistics, and access to rare processes where heavy flavors appear in association with electroweak bosons or in multi-jet topologies. That is how the extra quarks become precision tools rather than occasional curiosities. Now bring the question back to its sharpest form. If the visible universe is mostly built from up and down, why do we need the rest? One answer is that the standard model is not a model of what is common today. It is a model of what is allowed, what is forbidden, and what is produced when conditions change. The early universe changed conditions continuously as it cooled. Stars and supernovae create energetic environments where rare particles can be produced. Cosmic rays strike the atmosphere with energies that can reach far beyond what most natural environments provide. And human-built accelerators, while small on cosmic scales, create controlled conditions where these heavy flavors appear reliably. The presence of additional quark flavors is a statement about the universe's full phase space, not about the inventory that happens to dominate in room temperature matter. A second answer is that 3 generations appear to be tied to how the weak interaction produces CP violation, a measured asymmetry between matter and antimatter behavior in certain decays. You do not have to overreach into claims about baryogenesis to acknowledge the experimental fact that CP violation exists in the quark sector and that its structure depends on having at least 3 generations. This is not philosophical. It is a statement about what combinations of parameters can produce complex phases in the mixing description, and it is tested by decades of kaon and B-meson experiments. The extra quarks are not just extra mass. They are extra structure in how the universe permits transformations among flavors. A third answer is simpler and more unsettling. We do not yet know why the generations exist, or why their masses take the values they do. The standard model takes those masses as inputs. It predicts a vast amount once those inputs are set, but it does not explain them from first principles. That ignorance is not a weakness to hide. It is a map of where the frontier truly is. The universe is consistent enough to be described by a compact set of equations, and also strange enough to include repeated families of matter with dramatically different masses for no reason we can currently derive. If you keep listening with that in mind, the 6 flavors stop feeling like a pointless excess. They become a record of how the universe keeps the same rules while changing the conditions. Under ordinary conditions, the lowest mass options dominate, so up and down build stable nuclei. Under higher energies, nature reveals the rest of the spectrum not as a different physics, but as the same physics operating in regimes we rarely inhabit. There is one more point worth holding close, because it binds particle physics back to cosmology without stretching the evidence. In the early universe, heavy flavors were not exotic. They were part of the thermal population when temperatures were high enough. As the universe cooled, those flavors became Boltzmann suppressed, meaning they became rare because producing them required too much energy from the typical particle in the plasma. They did not need to be erased. They became statistically unlikely. Their disappearance was a predictable outcome of cooling. But the rules that allowed them never went away. They remain available whenever energy density rises again. That is why collider experiments feel like time machines in a precise sense. They do not take us back to the early universe as a whole, but they recreate specific energy scales and allow the heavy flavors to reappear on command. The spectrum is not a story about the past. It is a story about thresholds, and thresholds are universal. 6 flavors are not 6 independent worlds. They are stitched together by the strong interaction, and the strong interaction carries a charge unlike any other. A charge that must always balance to 0 in anything we can observe. A rule that is so strict, it shapes every hadron ever formed. The next part presses on that rule without mercy. Because once you accept 6 quarks, you still have to explain why each of them carries color, and why color is permitted to exist only in combinations that cancel perfectly, or matter itself cannot remain stable. Part 6. What is color in quarks, and why must it always cancel to nothing? There is a charge inside every proton that behaves so strictly that if it ever failed to cancel perfectly, the proton would stop being a stable unit of matter, and the universe you recognize would not assemble. When physicists say color in quantum chromodynamics, they are not describing a pigment, a wavelength, or anything your eyes can detect. Color is the name given to the strong interaction charge carried by quarks and gluons, the bookkeeping label that tells the strong force who is allowed to talk to whom and how intensely. It is the QCD analog of electric charge in electromagnetism, except it comes in 3 types rather than 1. and the force carriers themselves carry the charge. That last detail changes the entire personality of the interaction. In QED, photons carry no electric charge, so photons do not self-interact in the same direct way. In QCD, gluons do carry color charge, so gluons can interact with gluons. If you keep only that one difference in mind, many of the strange rules you have been meeting since Part 1 begin to lock into place. Confinement is not an extra rule pasted on top of quarks. It is what strong fields do, when the carriers of the force also carry the charge of the force. The historical path to color is one of those moments when physics improved because someone refused to accept a contradiction. In the early quark model, a proton was pictured as 3 quarks, and for a while that idea worked remarkably well as a classification scheme. But then a problem sharpened. Some baryons appeared to contain 3 quarks of the same flavor, in the same spatial state, with aligned spins, for example, the delta plus plus state, which in the simplest description would be up, up, up. If quarks are fermions, they must obey the Pauli exclusion principle. A naive 3 identical fermion picture seemed to violate it. Physicists could not treat that as a minor annoyance. If the spin statistic structure fails, you are not slightly wrong, you are fundamentally wrong. The resolution was to recognize that quarks carried an additional hidden degree of freedom, something that made those quarks not truly identical in the quantum sense. That extra label is what became color. The story is often told as a clean sequence. Oscar Greenberg introduced the idea in the mid-1960s as a way to restore consistency with quantum statistics, and shortly afterward, color was introduced explicitly as a gauge symmetry by Mu-Young Han and Yoichiro Nambu. The chronology matters because it shows color was not added for aesthetics. It was demanded by the logic of fermions and the observed baryon spectrum. Once you allow 3 color states for each quark, the Pauli conflict dissolves. The delta plus plus can be composed of 3 up quarks that differ in color, making the overall wave function antisymmetric in the hidden color part, even if the visible parts appear symmetric. That sounds technical, but the meaning is straightforward. Matter can remain stable because the quantum accounting can be made consistent without breaking the statistical rules that govern every fermion in nature. At this point, you might ask, why 3 colors? Why not 2 or 4 or 10? The best answer is not a story about preference. The answer is that 3 is what matches the observed patterns of hadrons and the measured structure of the strong interaction as a gauge theory with symmetry group SU3. QCD is a non-abelian gauge theory built on that SU3 symmetry. And in that structure, quarks come in 3 color states, while gluons occupy the 8-dimensional adjoint representation, which is why we speak of 8 gluons rather than 9. The details can be left inside the mathematics, but the output is testable. It predicts how quarks and gluons radiate, how jets form, and how hadrons emerge from high-energy collisions. Now we can face the second half of the title, the rule that color must always cancel to nothing in anything we can observe. This is the colorless condition, the reason hadrons are color singlets. A proton is not red, green, or blue. It is a specific combination of 3 quarks whose colors sum to a net 0 in the group theory sense. A meson is not a color either. It is a quark and an antiquark whose color and anticolor cancel into a singlet. The language red, green, blue is a mnemonic, not a picture, but it is a useful mnemonic because it reminds you that you need a complete balance rather than a plus-minus balance. This is where the strong interaction departs sharply from electromagnetism, in a way you can feel without equations. In electromagnetism, you can isolate a single electric charge. An electron can be trapped. A proton can be isolated. You can measure the field around it at macroscopic distances. In QCD, a single color charge never appears as an isolated, long-lived object at ordinary energies. The theory's dynamics ensure that any attempt to separate color produces new hadrons instead, because the energy in the color field does not disperse into space like the electric field does. It concentrates. That concentration is not a guess. It is reflected in what experiments see as jets and hadronization. When a high-energy collision produces a quark or gluon, the detector does not register that parton directly. It registers a collimated spray of hadrons, whose structure encodes the color charge of the initiating parton. The Particle Data Group review of QCD summarizes a key experimental fact that follows from color. Gluon-initiated jets are broader and have a softer particle spectrum than quark-initiated jets, as expected from perturbative QCD and the different color charges involved. That is not a small stylistic note. It is a direct, repeatable imprint of color charge and gluon self-interaction in real data. If you would like a sentence that keeps the story grounded in how a major laboratory communicates the idea, CERN's own description of heavy ion physics states plainly that quarks and gluons are color-charged, and because of color confinement, they cannot be isolated from hadrons in normal conditions, so hadrons must be colorless overall. That statement has no ornament. It is the operational rule that sits underneath nearly everything we do with QCD. So why must color always cancel in observable matter? The shortest answer is that the strong interaction does not allow color-charged states to propagate freely to large distances at low energies. In the language of field theory, only color singlet states appear as asymptotic states in the spectrum. In the language of experiments, you never detect a lone color charge arriving at a sensor. You detect hadrons, and that constraint holds whether you are observing the debris of a collider, collision, or the stable nucleons that build stars. This is also where your outline's phrase, that the universe demands perfect balance, becomes precise. It is not a moral demand. It is a dynamical consequence of the non-abelian gauge structure. Because gluons carry color, the field lines of the strong interaction can bind into flux tubes. Stretching those tubes stores energy in a narrow region. When enough energy is stored, the field converts energy into new quark-antiquark pairs, producing two color-neutral systems rather than one color-charged fragment. The outcome is that color leaks only into other color charges nearby, never into long-range free fields the way electric charge does. A common teaching summary echoed in particle physics lecture notes is that gluon self-interactions lead to confinement, and that all hadrons are color singlets, which is why only colorless combinations are observed. At this point, it is worth pausing on a subtlety that is easy to miss. Color neutrality is not the same thing as nothing is happening inside. A proton being colorless does not mean the strong field is absent. It means the net charge that would produce a long-range color field is zero. Inside, the strong field is intense. Quarks exchange gluons constantly. Virtual quark-antiquark pairs appear and disappear. Momentum and energy circulate through the system. The proton's stability is not a static stillness. It is a stable pattern maintained by QCD dynamics. This is one reason Part 4 could say correctly that most mass in ordinary matter is QCD energy, rather than the bare quark masses. Color is the charge that organizes that energy. There is also a practical payoff to understanding color as a charge rather than a metaphor. It explains why QCD becomes weaker at short distances and stronger at long distances. In non-abelian gauge theories, the vacuum polarization effects differ from QED because the gauge bosons interact with themselves. The result is asymptotic freedom at high energies and confinement at low energies, a link between color charge and the changing effective strength of the strong interaction as you vary the scale. You do not need the renormalization group equations to understand the meaning. The same interaction that prevents a free quark at low energy also allows quarks to behave quasi-free when struck at very high energy in deep inelastic scattering. That scale dependence is one of the reasons QCD is both powerful and hard. Now, connect this back to cosmology without stretching it. In the early universe, at temperatures of order trillions of Kelvin, matter existed in a quark-gluon plasma phase, where quarks and gluons were not bound into hadrons over long times. Even there, color was not absent. It was active in a dense medium. As the universe expanded and cooled through the QCD transition, color confinement took over and forced the degrees of freedom to reorganize into colorless hadrons. Later, those hadrons allowed nucleosynthesis to proceed, which then allowed atoms, stars, and galaxies. The bridge from microphysics to cosmic structure runs right through the bookkeeping of color. Here, one underlying pattern appears gradually unfolding across three connected layers. The first layer is definitional. Color is the strong interaction charge in QCD. The second layer is structural. QCD is an SU3 non-abelian gauge theory, which implies 8 gluons and gluon self-interactions. The third layer is empirical. Because of confinement, observable states are color singlets, and experimental signatures such as jet structure reflect the underlying color charge differences between quarks and gluons. Color is not an optional label. It is the mechanism that forces quarks to hide inside hadrons, and it is also the mechanism that makes certain tiny asymmetries in quark behavior measurable, because once you have multiple generations and a structured charge system, the weak interaction can treat flavors differently in ways that leave traceable differences in decay patterns. And once color is understood as the rule that locks matter into stable neutral structures, another imbalance comes into view. This one does not involve confinement, but transformation. In rare, precisely measured cases, quarks change under the weak force in ways that are not perfectly symmetrical, is less than #0. 5 is greater than. And within that small unevenness lies a much larger consequence, whether matter could persist long enough for galaxies to form at all, rather than dissolving into an almost uniform field of radiation. Part 7. Did quarks decide that matter would exist at all? If the early universe had been even slightly more symmetric than it is, every proton and neutron you have ever heard of would have been erased into light, and the sky would hold almost nothing but an afterglow, with no galaxies to form and no stars to ignite. The reason that statement is scientifically sharp is that we can measure how close the universe came to that fate. From the cosmic microwave background, Planck's final results pin down the physical baryon density with high precision, with a best fit value of omega sub bh squared is approximately 0.0224. That number is a modern observational way of saying the universe contains a small but definite amount of ordinary matter, the kind built from protons and neutrons. But when cosmologists translate that matter density into a particle counting language, it implies something almost uncomfortable in its simplicity. For roughly every billion photons in the universe, there is only about one excess baryon. The universe is not strongly matter-dominated in its raw bookkeeping. It is barely tipped, and that tiny tip is the only reason there was any material left after the era when matter and antimatter annihilated each other at enormous rates. So where could such a small imbalance come from, without asking for miracles or special initial conditions? This is where quarks enter the story again, not as building blocks inside protons, but as participants in processes that treat matter and antimatter slightly differently. The central idea is CP violation. CP is the combined operation of swapping particles with antiparticles and reflecting space as if in a mirror. If the laws of physics treated matter and antimatter with perfect symmetry, then for every process creating a little more matter, there would be a mirror process creating a little more antimatter, and the net outcome would cancel. The surprise is that nature does not obey perfect CP symmetry. It breaks it measurably in the quark sector. This was not guessed first and confirmed later. It was discovered in a specific experiment with a specific beamline, and the historical details matter because they show how small the effect is and how careful the confirmation had to be. In 1964, James Cronin, Val Fitch, Jim Christensen, and René Turlet performed an experiment at Brookhaven's alternating gradient synchrotron using neutral kaons. In the simplest symmetry picture of that time, the long-lived neutral kaon should almost never decay into two pions, because that decay would signal the wrong CP character. Yet the team observed exactly that rare decay mode, forcing the conclusion that CP symmetry is not exact in nature. The effect was tiny at the level of parts per thousand, but it was real. The universe had revealed a built-in asymmetry between matter and antimatter. Cronin later emphasized how this discovery continues to press on the foundations, noting in his Nobel lecture that CP violation is telling us that there is a fundamental asymmetry between matter and antimatter, and that we must keep seeking its origin. That sentence matters because it captures the correct scientific posture. We have evidence for CP violation. We have multiple ways to measure it, but we still do not have a complete explanation for why it takes the form and strength it does, or whether it is enough to account for the cosmic matter surplus. Now bring quarks into focus. Kaons are made of a strange quark, paired with a down antiquark or the antiparticle combination. The 1964 kaon experiment was not about quarks in the way modern collider physics is, but in today's standard model language, it was an observation of how quark flavors mix, and how that mixing permits CP violating phases. By the 1970s and 1980s, the theoretical framework matured into the CKM description of quark mixing, and it made a clean prediction that CP violation should also appear in B mesons particles containing bottom quarks. That prediction set the stage for a new generation of experiments designed specifically to overconstrain the quark mixing picture and measure CP violation in multiple independent channels. 2 dedicated B factories were built for this purpose: Babar at SLAC in the United States and Bell at KEK in Japan. These machines and detectors were not small tabletop devices. They were large-scale facilities with accelerator rings and beamlines measured in hundreds of meters, engineered to produce huge numbers of B mesons and track their decays with extreme precision. Their goal was to measure time-dependent CP violation, especially in decays like B0, decays to J psi K sub s, which are particularly clean for extracting the CP violating parameters of the quark sector. That effort succeeded. By the early 2000s, the B factories established large CP violating effects in the B system, consistent with the CKM framework. Even without writing a single equation, the meaning is direct. The weak interaction allows quarks to change flavor, and in that flavor-changing process, the probabilities for matter and antimatter pathways are not identical. That difference is measurable, repeatable, and now part of the core evidence base of particle physics. Then came the LHC era. At CERN, the LHCb experiment was designed to study heavy flavor physics at high rates, with exquisite vertexing and particle identification, and it has delivered a long sequence of CP violation measurements in systems involving bottom and charm quarks. The details vary by channel, but the underlying message repeats. Quark processes are not perfectly symmetric under CP, so CP violation exists. It is real. It involves quarks. Why does that matter for cosmology? Because in 1967, Andrei Sakharov wrote down a remarkably compact set of conditions that any successful mechanism for generating a matter-antimatter imbalance must satisfy. They are now called the Sakharov conditions. You need processes that can change baryon number. You need C and CP violation, and you need a departure from thermal equilibrium so that forward and reverse reactions do not erase the net effect. This is not a complete model. It is a set of necessary conditions, a filter. If a proposed early universe process lacks any one of them, it cannot produce the observed matter surplus from a symmetric start. The presence of CP violation in quark physics therefore does something important. It tells us that one of the required ingredients is present in the laws of nature. The universe does permit CP violation. The next question is harder and far more constraining. Is the amount and form of CP violation in the Standard Model sufficient to account for the observed baryon asymmetry of the universe? This is where the story stays careful, because the honest answer is not a victory speech. In mainstream cosmology and particle physics, the measured CP violation in the quark sector within the Standard Model appears too small to generate the observed cosmic asymmetry through simple Standard Model processes alone. That is one reason baryogenesis remains an open research frontier, motivating searches for new sources of CP violation, new interactions, or new phases in the early universe that could satisfy Sakharov's conditions more effectively. It is also why Cronin's remark that the origin remains a mystery has not aged out. Still, it would be a mistake to treat quark CP violation as irrelevant. It is the only confirmed example we have of CP violation in particle interactions. It is a proven fact that the universe's laws do not enforce perfect matter-antimatter symmetry. That alone changes the logic of the early universe. To make this feel less abstract, consider what the early universe was actually like during the first seconds. It was a dense plasma of particles and radiation, with reactions occurring at astonishing rates. In thermal equilibrium, every reaction that makes a baryon has a reverse reaction that destroys it, and the net baryon number stays near zero if the fundamental laws preserve symmetry. But if CP symmetry is violated, the forward and reverse reaction rates can differ slightly when certain conditions are met. If on top of that baryon number is not absolutely conserved in the relevant processes, and if the plasma is driven out of equilibrium by rapid expansion or phase transitions, then tiny biases can accumulate into a residual baryon number. That chain is the reason cosmologists keep returning to the quark sector and to early universe phase changes such as the electroweak transition. Even if the Standard Model's own CP violation is not enough, the structure of the quark sector shows what kinds of mechanisms are physically plausible. It is a guide to what nature already knows how to do, and therefore what a successful baryogenesis model is likely to resemble. There is a second cosmology link that is just as important and often overlooked. If matter and antimatter had annihilated almost completely, you would still have radiation. You would still have photons. You would still have a cosmic microwave background, but you would not have the baryonic scaffolding needed for stars, planets, and chemistry. The existence of galaxies, therefore, does not merely tell us gravity works. It tells us there was leftover matter for gravity to work on. When Planck measures the baryon density, it is indirectly confirming that the early universe did not erase its baryons. Now bring the human story back in, because the emotional weight in this part is not sentimental. It is the weight of how fragile the matter inventory is. The Kaon experiment in 1964 had to detect an extremely rare decay in the presence of backgrounds using the technology of its era, and to convince a skeptical community that the effect was not an artifact. The CERN Courier's historical account of the early days emphasizes that the apparatus was built in a neutral beamline inside the AGS ring, and that the result had to survive deep scrutiny before acceptance. The B factories then spent years building datasets and reducing systematic uncertainties to establish large CP violation in B decays. LHCb has continued the same discipline, with enormous statistics and careful control of detector-induced asymmetries. This matters because cosmology is often criticized as being too far from laboratory control. But here, cosmology's central question about why matter exists is being attacked from both ends. From the sky, Planck locks down the baryon density and the early universe conditions with high precision. From the ground, accelerator experiments measure the symmetry violations that might plausibly seed a baryon surplus. The two lines of evidence do not yet meet in a fully closed loop, but they are no longer separate stories. Now keep one last scientific pressure point in view. CP violation in quarks is real, but it does not automatically solve baryogenesis. The Sakharov conditions are necessary, not sufficient. Many specific mechanisms have been proposed over the decades, from electroweak baryogenesis to leptogenesis and beyond, and each one has to satisfy observational constraints, including limits on new particles and new CP violating effects. The universe is not generous here. It allows only a narrow corridor for new physics, because so much is already measured so well. So the role of quarks in this part is not to claim that quarks decided the universe's fate. It is to show that the only confirmed crack in perfect matter-antimatter symmetry lives in the quark sector, and that crack is a candidate ingredient in whatever early universe process produced the small baryon surplus that Planck measures indirectly today. If you want the cleanest way to hold this in your mind without equations, keep two facts side by side. First, the cosmos contains a small but definite amount of baryonic matter fixed tightly by CMB observations. Second, particle physics has measured processes where matter and antimatter do not behave identically, and those processes involve quarks and the weak interaction. Between those two facts lies the central, unfinished bridge, and there is a final connection to make before this part releases into the next one. Even if the baryon surplus was created in the first fractions of a second, that surplus only becomes visually meaningful much later, when baryons cool, form atoms, and finally assemble into stars, where nuclear reactions rewrite quarks inside, protons and neutrons into new elements. The next part therefore turns from the origin of the surplus to the long, slow consequence, asking how quarks can govern the life cycles of stars and the growth of galaxies while never appearing as free particles in space. Part 8. Why can quarks shape stars and galaxies without ever leaving the proton? A single flip inside a proton, one up quark becoming a down quark through the weak interaction, is the difference between a universe filled with long-lived stars and a universe that stays dark, cold, and chemically simple. That statement sounds too large for something so small. So let's earn it, step by step, using only things that have been measured, tested, and repeatedly confirmed. When we say quarks never leave the proton, we are recalling confinement, the rule that color-charged particles do not appear as isolated objects under ordinary conditions. Yet when we say quarks shape stars and galaxies, we are pointing to a different kind of influence. Quarks determine the identities and properties of protons and neutrons. Protons and neutrons determine nuclear physics. Nuclear physics determines how stars shine, how long they live, what elements they build, and how those elements change the cooling of gas that later becomes galaxies and planets. Quarks stay hidden, but the rules they obey are built into every rung of the cosmic ladder. Begin with the smallest practical unit of stellar life, the hydrogen nucleus. A hydrogen nucleus is a proton, and a proton is a bound state whose internal dynamics are set by quarks and gluons. Part 4 already established the crucial fact that most of the proton's mass is not the sum of quark bare masses, but the energy of confinement, motion, and field stress inside the hadron. That matters here because stars are engines that convert small differences in nuclear binding energy into radiation over vast times. Those binding energies are set by the strong interaction and by the proton and neutron masses. Both are QCD outcomes. If the QCD scale were different by even a modest fraction, the stability and binding of nuclei would change. The energy release per fusion reaction would change, and stellar evolution would not look like it does in our universe. Now, what is the first fusion step in a star like the Sun? It is not two protons simply snapping together into helium. That would violate multiple conservation rules. The actual starting point is the proton-proton chain, and its first step is slow on purpose. Two protons approach closely enough that the strong interaction can act. One of the protons must transform into a neutron so that the pair can form deuterium, a bound state of one proton and one neutron. That transformation is a weak interaction process. In quark language, it is an up quark turning into a down quark with a positron and a neutrino emitted to conserve charge and lepton number. Without that quark-level flavor change, the deuterium bottleneck does not open, and the main fuel of normal stars never ignites in a stable way. This is not an abstract story. It is the reason the Sun can burn steadily for about 10 billion years, rather than exhausting itself in a short outburst. The weak interaction is weak, meaning the conversion is rare, meaning the reaction is slow, meaning a star can shine for billions of years. Stellar longevity is a consequence of a quark-level rule that limits how quickly protons can be turned into neutrons under stellar conditions. The historical path to understanding this was not quick. In the late 1930s, Hans Bethe worked out how stars produce energy through nuclear reactions, identifying pathways like the proton-proton chain and the CNO cycle. The work was not merely theoretical elegance. It was an attempt to explain why stars shine at the rates they do and why their lifetimes fall into the ranges inferred from stellar populations. When you look at an old globular cluster and infer ages of around 10 billion years, you are reading a consequence of the weak interaction's slowness, and that slowness is tied to the quark flavor structure of the Standard Model. At this point, it is important to separate two ideas that people often blend. Quarks do not do fusion. Nuclei fuse through the strong interaction balanced against the electromagnetic repulsion of protons. But the availability of neutrons, the existence of deuterium, the stability of helium, and the network of nuclear reactions depend on the proton-neutron system, and that system depends on quark identities and on QCD dynamics. Consider the neutron itself. A free neutron decays with a mean lifetime of roughly 15 minutes, turning into a proton, an electron, and an antineutrino. That decay is again a quark-level transition, but inside a nucleus, neutrons can be stable because the total nuclear binding makes certain configurations energetically favored. This stability is what allows the periodic table to exist. The balance of protons and neutrons in stable nuclei is a balance of forces and energies that ultimately trace back to QCD and electroweak physics. Even the fact that the neutron is slightly heavier than the proton matters enormously. If the neutron were lighter than the proton could decay into a neutron, and hydrogen as a stable element would be threatened. If the mass difference were much larger in the opposite direction, deuterium could become unstable, and the first step of stellar fusion would be blocked. The measured proton and neutron masses and their difference are not decorative details. They are boundary conditions for chemistry and for the existence of long-lived stars. Now move outward from a single star to the chemical evolution of a galaxy. Stars do not merely shine, they manufacture elements. The first generation of stars formed from mostly hydrogen and helium produced in Big Bang nucleosynthesis. Those early stars, through fusion and later through explosive deaths, built heavier nuclei such as carbon, oxygen, silicon, and iron. These elements are then returned to the interstellar medium through stellar winds and supernova explosions. Over billions of years, this enrichment changes how gas cools. Heavier elements provide more pathways to radiate energy away, allowing gas clouds to lose thermal support and fragment more efficiently. That is one reason later generations of stars can form with lower masses and in different environments. The galaxy's ability to evolve a diverse stellar population depends on the existence of nuclear binding and the specific energy levels and reaction pathways of nuclei, which again depend on the strong interaction and on the proton-neutron system. A famous example is the production of carbon in stars through the triple alpha process. Two helium nuclei can form beryllium-8, which is unstable, but for a brief time, it can exist long enough for a third helium nucleus to collide and form carbon-1,2. The efficiency of this process depends strongly on resonant energy levels in carbon-1,2, a fact emphasized by Fred Hoyle, who predicted an excited state to explain the observed abundance of carbon in the universe. That prediction was later confirmed experimentally. This is not a story about quarks as separate particles. It is a story about how the strong interaction shapes nuclear structure and therefore shapes cosmic chemistry. Without carbon production, the chemical inventory of galaxies would look radically different. Now return to the title's central tension. If quarks never leave the proton, how can they shape objects as large as galaxies? The answer is that galaxies are built from the gravitational behavior of matter, and the gravitational behavior of ordinary matter is dominated by the rest masses and interaction properties of baryons, which are QCD-bound states. The mass of baryons affects how baryonic matter responds to gravity, how it couples to radiation in the early universe, and how it later collapses into stars and galaxies. The detailed pathway from small density fluctuations in the early universe to large-scale structure involves dark matter as the main gravitational scaffold, but the visible content, the stars and gas, are baryonic. Baryons are protons and neutrons. Their masses, stability, and nuclear reactions are the bridge from cosmology to astrophysics. There is another layer where quarks matter without appearing: neutrinos. In the proton-proton chain, neutrinos carry away energy and provide a direct signature of fusion. The solar neutrino problem, first revealed in the late 20th century, was a major scientific puzzle because detectors on Earth measured fewer solar neutrinos than predicted. The resolution involved neutrino oscillations, but the origin of the neutrinos remained the same. They are created when protons are converted to neutrons in the Sun's core, a process that begins with quark flavor change. When modern experiments measure solar neutrinos, they are sampling the quark-level gate that controls stellar burning. The neutrino is not carrying a picture of a quark, but it is carrying evidence that quark identities are being rearranged inside stellar cores. Now connect this to the timescales in your outline. Nuclear fusion releases energies of order millions of electron volts per reaction, while stars live for billions of years. The way these numbers can coexist is that each fusion event releases a modest amount of energy, and the rate of events is regulated by both the tunneling through the Coulomb barrier and by the slow, weak interaction step that makes deuterium. A star is a self-regulating system. If the core heats up, reaction rates increase, pressure rises, and the star expands, cooling the core. If the core cools, reactions slow, gravity compresses it, and the core warms. The stability of this thermostat relies on the existence of stable nuclei and predictable reaction networks. Those networks rest on hadronic physics. There is also an extreme regime where quark physics may become more direct, and it sits at the boundary between stellar astrophysics and high-density QCD, neutron stars. When a massive star collapses and forms a neutron star, matter is compressed to densities above those found in atomic nuclei. In that environment, the arrangement of baryons may shift. Hyperons, containing strange quarks, could appear. More exotic phases of dense matter have been proposed, including forms where quark degrees of freedom become less confined. Observations of neutron star masses, radii, and tidal deformabilities constrain these possibilities. Even without asserting which phase is realized, the logic is clear. The existence of heavier quark flavors like strange is not irrelevant to the cosmos. It may become relevant again in the most dense stellar remnants. So the universe has at least two operating regimes. In ordinary stars and gas clouds, quarks influence reality indirectly through hadrons and nuclei. In the densest remnants, quark physics may become closer to the surface, not as free quarks flying through space, but as changes in the equation of state of matter at nuclear densities. That equation of state is what determines how a neutron star supports itself against gravity and how it responds in mergers. When gravitational wave observatories record signals from neutron star mergers, they are, in part, recording constraints on the behavior of QCD matter under conditions impossible to reproduce on Earth at the same scale. At this stage, a careful listener might ask a sharp technical question. If quark confinement hides quarks, why is the language of quarks useful in astrophysics at all? The answer is that the quark description is not used because it is visually direct. It is used because it is the most accurate fundamental description we have of hadronic matter. Nuclear models are effective descriptions built on top of QCD. They work because QCD, when coarse-grained to nuclear scales, produces the forces and symmetries that nuclear physics uses. When astrophysics asks about fusion chains, binding energies, neutrino production, and dense matter, it is asking about outcomes that depend on QCD, whether we mention quarks or not. Quarks are the underlying degrees of freedom that make those outcomes consistent across environments. So Part 8's answer can be stated in one clean line. Quarks shape stars and galaxies because quarks determine the properties of protons and neutrons determine nuclear physics. And nuclear physics sets the energy release lifetimes and chemical enrichment that drive cosmic evolution, all while confinement prevents quarks from appearing as isolated particles. Keep one more detail close, because it is easy to underappreciate. The stability of matter at cosmic scale depends on delicate balances between forces that do not look delicate in their equations. The strong interaction must be strong enough to bind nuclei. Electromagnetism must be strong enough to set chemistry and to resist fusion until cores are hot enough. The weak interaction must be weak enough to slow the first step of hydrogen burning. Gravity must be weak enough that stars do not collapse instantly, yet strong enough to gather gas into stars at all. In the center of that balance, hidden behind confinement, the quark identities and the field dynamics of QCD set the baseline properties of the baryons that carry ordinary mass, and now the connection forward can be stated without breaking the calm pace. Once you see quarks shaping the longest-lived engines in the universe, while remaining unobservable as individual objects, it becomes harder to treat them as the final layer by habit alone, because physics has a long record of finding deeper structure beneath whatever seemed fundamental at the time. Part 9. Are quarks the final layer of reality, or just the last one we can touch? Quarks sit at the end of our microscope like a locked door, because every time we have ever believed we reached the smallest layer, nature answered by showing us a deeper mechanism, hiding underneath the layer we thought was final. It is worth starting from a simple fact that has survived every modern test. In every high-energy experiment, where we probe matter with increasing resolution, quarks behave like point-like constituents, down to the smallest distances we can currently access. That statement is not a slogan. It is an experimental conclusion built from decades of scattering measurements and collision data, and it is also framed carefully because point-like in physics means no internal size detected within current limits, not proven to have no size. The difference matters. The most direct way we test is there something inside a quark is to look for deviations from the standard model predictions that would appear if quarks were composite. If quarks had substructure, then at sufficiently high energies, new effective interactions would appear, often modeled as four-fermion contact terms, because at energies below the binding scale, the detailed internal dynamics compress into a short-range interaction. The Particle Data Group's 2025 review on quark and lepton compositeness describes this logic, plainly emphasizing that if fermions are made of constituents, then new interactions appear at a compositeness scale, L, and at energies much lower than L. The effects show up as suppressed contact terms. Now compare that expectation to what the LHC actually sees. When ATLAS and CMS measured dijet angular distributions and high transverse momentum jet spectra, they are watching for precisely the patterns. Contact interactions would produce a more isotropic scattering signature and excesses in the tails relative to perturbative QCD predictions. The same PDG review summarizes that over 3 decades, including the LHC at 13, TeV experiments, have searched for these signatures using jet final states, specifically with angular distributions of the highest PT jets and inclusive jet spectra. The important part is the outcome. The newest limits do not show evidence of compositeness. They set lower bounds on Lear. The numbers are strong enough that they carry real meaning even without equations. In the PDG 2025, review limits from combined dilepton channels are quoted at the level of tens of TeV for certain contact interaction models, and CMS limits using a 140 FB to the power of -1 dataset at 13 TeV, about 24 TeV to about 36 TeV, depending on the chiral structure and whether interference is constructive or destructive. These are not decorative thresholds. If quark substructure exists, the binding scale is being pushed higher and higher, meaning any internal constituents would be hidden behind energies that current experiments have not yet reached. This is why quarks occupy such a strange position in physics. They are simultaneously deeply real and deeply inaccessible. We infer them as constituents from scattering. We see their fingerprints in jets. We reconstruct their flavor and charge through decay chains, and we can model their dynamics with extraordinary precision in QCD. Yet confinement prevents us from isolating them, and our direct probes still see no internal structure. If that sounds like a reason to declare victory, history suggests caution. Physics has a habit of becoming confident right before new instruments rewrite the boundary. In the 19th century, atoms were debated as a useful model rather than a confirmed physical entity. Then Brownian motion kinetic theory and later electron discovery made atoms unavoidable. Early 20th century physics treated atoms as fundamental building blocks until nuclear scattering experiments revealed a compact nucleus. The nucleus then looked like a plausible endpoint until the discovery of the neutron and the development of nuclear models revealed structure. In the 1960s, the Hadron Zoo suggested something deeper and deep inelastic. Scattering at SLAC revealed parton-like constituents inside the proton, which we now identify with quarks and gluons. The pattern is not that nature hides forever. The pattern is that the next layer tends to appear when the tools become sharp enough and the questions become constrained enough to force it. So Part 9 is not a promise that quarks are composite. It is a disciplined way to ask what would count as evidence either way, and why cosmology, which often speaks about the largest scales, has a stake in that question. Start with what we know that quarks cannot explain by themselves, even if they are fundamental. The standard model with quarks at its core still leaves several cosmological facts as inputs rather than derivations. One is dark matter, another is dark energy, another is the origin of the matter asymmetry discussed in Part 7, another is the origin of neutrino masses, another is the initial condition that set the near uniformity of the early universe and seeded the small density fluctuations that later became galaxies. These are not poetic mysteries. They are specific gaps between an extremely successful microscopic theory and the measured cosmic inventory. That is why the title says, Cosmology hesitates. Cosmology is not hesitating because it lacks data. Modern cosmology has data at a level of precision that would have seemed impossible a few generations ago. It hesitates because precision is now revealing where the standard model's completeness does not extend. Even the parts of cosmology that look settled can generate friction when new observatories push into new regimes. A clean example is the discussion around very high redshift galaxy candidates in early JWST results. Some analyses argued that early candidates could imply unexpectedly high stellar masses at very early times, raising questions about consistency with standard galaxy formation in LCDM. This topic remains technical and actively discussed because photometric redshifts, lensing completeness, and stellar population modeling all matter. But the important connection for this part is not whether any one early dataset breaks LCDM. The connection is that each new instrument pushes cosmology into parameter space, where the models must earn their confidence again, just as particle physics has to earn confidence again when it pushes to higher energies. Now return to quarks and ask the hardest version of the question. If quarks are fundamental, then why do they come in 3 generations with masses that span orders of magnitude? And why do the mixing angles and CP violating phase take the values they do? The standard model does not predict these numbers. It takes them from experiment. That is not a minor incompleteness. It means we have a theory that predicts an enormous amount once the parameters are inserted, but it does not explain why the parameters are what they are. In past eras, parameters we measure but do not derive have often been the place where deeper structure eventually appears. Not always, but often enough that it becomes a rational target. So what would quark structure look like experimentally? There are several broad possibilities, and modern searches take them seriously without committing to any one story. One possibility is contact interactions already discussed, where new short-range forces appear because quarks are composite. This is exactly what dijet and dilepton analyses constrain, and the PDG's limits at tens of TeV show that if this is the correct direction, nature is hiding the scale well above current energies. A second possibility is excited quarks heavier partners that would exist if quarks have internal constituents that can be excited into higher energy configurations. Analogous in spirit to excited atomic states, but at a much deeper level. The PDG Compositeness Review includes a section on limits on excited fermions, describing how such states could be produced via contact interactions and also coupled to gauge bosons like gluons. So far, the experimental outcome is again the same pattern. Searches set lower mass limits and exclude regions of parameter space, but do not produce a confirmed signal. The third possibility is that quarks are not composite, but the standard model is embedded in a larger framework that changes behavior at energies not yet reached, such as grand unification, extra symmetries, or other, beyond standard model physics. In that case, quarks can remain fundamental while still not being final because the deeper layer would be in the structure of the laws rather than in the structure of the particles. That idea is already partially motivated by known facts. Neutrino masses require physics beyond the minimal standard model. Dark matter requires at least one new component beyond the standard model's particle list. And the smallness of CP violation in the quark sector, relative to what baryogenesis might require, is one of the motivations for searching for new CP violating sources. Now, a careful listener might ask for a practical, testable anchor. Where exactly are we looking? And what is the clearest evidence that quarks are for now the last layer we can touch? The clearest evidence is that high-energy scattering keeps matching the Standard Model's point-like description within tight uncertainties, and the deviations that compositeness would produce are being pushed out to higher and higher scales. The PDG's description of LHC jet searches and the quoted L limits in the tens of TeV range are a concise way of capturing that. If quarks have size, it is smaller than the effective resolution scale implied by these bounds, and any internal constituents are confined behind energies not yet directly accessible. Another anchor is that QCD, the theory that governs quarks and gluons, is extraordinarily successful across multiple regimes, from collider jet physics to lattice calculations of hadron properties. That success does not prove quarks are fundamental, but it does mean that if there is deeper structure, it must reproduce QCD's results with extreme accuracy at accessible scales, just as quantum electrodynamics must reproduce the classical electromagnetic limit. Nature is allowed to be deeper, but it is not allowed to be sloppy where we already have precision. Cosmology contributes a complementary anchor. If new physics exists beyond the Standard Model, it is likely to leave traces in the early universe, in the growth of structure in relic abundances, or in subtle deviations in cosmic observables. JWST's reach into the early era of galaxy assembly is one example of how cosmology keeps extending its empirical boundary. Again, the point is not to claim that early galaxies demand new physics. The point is that cosmology has become an arena where new physics could in principle show itself, because the early universe naturally explored energies and densities beyond what we can sustain in laboratories. So where does that leave the question of whether quarks are final? It leaves it in a place that is scientifically stable and honestly incomplete. Quarks appear elementary in every direct test so far. The strongest collider limits do not reveal compositeness. They push the relevant scales upward into the tens of TeV for certain effective interaction models. At the same time, the Standard Model, with quarks as elementary inputs, does not explain several measured cosmic facts, including the dark matter content and the origin of the baryon asymmetry, and it does not derive the pattern of quark masses and mixings from first principles. Those gaps do not imply quarks are composite, but they do imply that calling quarks the final layer would be premature. There is one more reason the title's phrasing matters. The last one we can touch is not just about accelerator energy. It is also about the method. Quarks can be touched through scattering because they carry electric charge and color charge, and those charges leave measurable signatures. But not every fundamental degree of freedom is obliged to couple to us that strongly. Dark matter, if it exists, as particles might couple weakly enough that it becomes hard to touch, even if it is abundant. The universe can contain layers that are not easily interrogated by the same tools we use for quarks. Cosmology, therefore, has to stay flexible. It is trying to infer unseen components from gravitational effects, while particle physics tries to produce unseen components in collisions. The two approaches can converge, but neither one gets to assume the endpoint. If you want a single concrete image to hold as this part closes, hold a modern collider event display in your mind, not as spectacle, but as a measurement. You collide protons, you reconstruct jets, you compare angular distributions to QCD predictions, and you search for the small systematic distortions that compositeness would cause. You do the same with dileptons, looking for contact interaction distortions at the highest invariant masses. The result is not, we found a smaller thing. The result is the boundary moved again. And with that boundary in place, the final part can turn the question around in a more physical way. If quarks are not merely ingredients inside matter, but the load-bearing framework that makes atoms, chemistry, and stars possible at all, then removing them is not a thought game. It is a controlled way to see what parts of the universe collapse first, and what, if anything, could remain when the most familiar layer is taken away. Part 10. If quarks never existed, would space itself still make sense? If quarks had never existed, the universe would not merely look different. It would fail to organize itself into anything that could be recognized as structure, history, or persistence. This is not a philosophical claim. It is a physical one, and it can be tested by carefully removing quarks from every process we know and watching step by step which layers of reality collapse first. When cosmology asks what is fundamental, it does not ask in the abstract. It asks what must remain intact for time to progress, for energy to localize, and for information to be stored in durable forms. Quarks turn out to sit at the base of all three. Begin with the simplest consequence. Without quarks, there are no protons and no neutrons. Without protons, there are no hydrogen nuclei. Without neutrons, there are no stable atomic nuclei beyond hydrogen. Even if hydrogen could somehow exist, atomic structure ends before it begins. Electrons may still exist as leptons, but without positively charged nuclei to bind to electrons, have nothing to orbit. Atoms disappear not because chemistry fails, but because the concept of chemistry never forms. At this point, it might sound as though the universe simply becomes emptier. That is not accurate. It becomes simpler in a way that prevents complexity from ever emerging. A universe without quarks would still contain radiation. It would still contain space-time. It might still contain fields, but it would lack the ability to trap energy in localized, persistent configurations. The disappearance of quarks removes the universe's ability to build long-lived matter. The earliest universe already gives us a preview of this state. In the first fractions of a second after the Big Bang, matter did not exist in its familiar form. The universe was filled with radiation and a quark-gluon plasma, an environment so hot and dense that individual hadrons could not form. As the universe expanded and cooled, quarks became confined into protons and neutrons. That transition was not decorative. It was the moment when energy stopped behaving like a smooth bath and started becoming countable, localized, and stackable into structures that could survive expansion. If quarks never existed, that transition never occurs. The universe remains radiation-dominated indefinitely. Expansion continues, temperature drops, but there is nothing that can clump into stable objects beyond transient fluctuations. Gravity still exists, but gravity alone cannot create structure out of radiation efficiently. Radiation pressure resists collapse. Without massive particles to anchor gravitational wells, space-time remains thinly populated and dynamically sterile. Now remove the next layer. Without protons and neutrons, stars cannot form. Stars are not merely luminous objects. They are the engines that give the universe memory. A star integrates time. It converts mass into radiation slowly and predictably over billions of years. That slow conversion allows the universe to develop eras. Without stars, there are no long clocks. There are only brief interactions and continuous dilution. It is worth pausing on that idea of memory because it is one of the least obvious consequences of quarks. Memory in physics does not mean consciousness or biology. It means the ability of a system to store information about past conditions in stable configurations. Atomic nuclei store information in their isotopic ratios. Crystals store information in lattice defects. Planets store information in layered compositions. Galaxies store information in stellar populations of different ages. None of these are possible without baryonic matter, and baryonic matter is impossible without quarks. A universe without quarks cannot remember its past in any durable way. It can only evolve smoothly from one radiation-dominated state to another. Now consider cosmic chemistry. Every element heavier than hydrogen is built inside stars or during violent stellar deaths. Carbon, oxygen, nitrogen, silicon, iron, all of them are products of nuclear fusion and nucleosynthesis pathways that rely on the strong interaction and on the existence of stable protons and neutrons. Remove quarks, and these pathways never open. The periodic table collapses before it is written. This is not a small loss. Chemistry is not an optional feature of the universe. Chemistry is how energy differences become complex arrangements. It is how cooling becomes efficient. It is how matter differentiates into phases. Without chemistry, gas cannot cool efficiently, and without cooling, gravitational collapse stalls. Galaxies struggle to form stars, even if dark matter exists to provide gravitational scaffolding. The visible universe becomes a sparse, glowing fog without internal articulation. Now consider spacetime itself. The title asks whether space would still make sense without quarks. The answer is subtle. The equations of spacetime still exist. General relativity does not require quarks to be mathematically defined. But meaning in physics is not only about equations. It is about what the equations act upon. Spacetime curvature responds to energy and momentum. In a universe with only radiation, spacetime responds, but the response is smooth and quickly diluted by expansion. There are no dense, persistent stress-energy concentrations that can anchor long-lived curvature features like stars, planets, or galaxies. The geometry remains simple, almost forgetful. Without quarks, spacetime loses its ability to carry detailed structure across time. Even black holes, which can form from radiation under extreme conditions, behave differently in such a universe. Radiation-dominated black holes evaporate quickly relative to cosmic timescales. They do not anchor long histories of structure formation. They do not seed galaxies. They are brief punctuation marks in an otherwise uniform expansion. At this point, it becomes clear why quarks can be described as load-bearing. In architecture, load-bearing elements are not the most visible. They are the components without which the building collapses, even if walls and decorations remain. Quarks play that role in reality. They are not the things we touch directly. They are the reason anything can be touched at all. This perspective also clarifies why cosmology treats the Standard Model with both confidence and restraint. The Standard Model does not explain everything. It does not explain dark matter. It does not explain dark energy. It does not explain why the universe began in the state it did. But it does explain why once the universe cooled past a certain point, complexity became possible. Quarks are central to that explanation. There is a historical parallel worth recalling here. In the early 20th century, physicists debated whether atoms were real or merely calculational devices. Once atoms were accepted as real, the deeper question emerged. What would the world look like without them? That question revealed that solids, liquids, chemistry, and thermodynamics all depended on atomic structure. The same logic now applies one layer deeper. We can ask what remains if quarks are removed, and the answer is not a simpler universe, but a universe incapable of building. This also reframes the journey you have taken through all 10 parts of this series. We began with confinement, the rule that forbids isolated quarks. We moved through fields, early universe conditions, mass generation quark families, color charge, asymmetry stars, and the question of whether quarks are final. The arc leads here not to a claim of completeness, but to a recognition of dependence. Quarks do not need to be ultimate to be essential, and that distinction matters. Science does not require that we know the final layer to understand the function of the layers we can reach. Bridges stand, even if we do not know the atomic structure of every bolt. Likewise, cosmology can describe galaxies, stars, and chemical evolution precisely because the quark layer behaves in a stable, predictable way across the observable universe. One final point brings this full circle. When we look out with modern observatories and see galaxies billions of light-years away, we are not just seeing light. We are seeing the long-term consequences of quark-level rules applied consistently across cosmic time. Every spectral line, every stellar population, every chemical fingerprint is a delayed echo of quarks doing what they always do everywhere. So if quarks never existed, space would still be there, time would still pass, and radiation would still flow. But the universe would lack accumulation, differentiation, and continuity. It would have motion without memory, expansion without architecture, and energy without structure. That is why quarks are not merely components of reality. They are the framework that allows reality to hold together long enough to become interesting. And as this long exploration comes to rest, I want to thank you for staying with this journey from the smallest rules of confinement to the largest consequences for the cosmos. If this long journey through the quiet structure of the universe has brought you even a small sense of calm, thank you for spending this time here with me. A gentle like or a soft tap on subscribe is a simple way to let me know these stories are worth continuing. And wherever you're listening from tonight, I wish you a peaceful rest and a very good night.